To make wind energy competitive with fossil fuels, it is essential to reduce its cost significantly. In this regard, energy experts predicts significant reductions in the levelized cost of energy (LCOE) for wind power by 2035 and 2050 compared to 2019 baseline values as shown in this graph. Across the three wind applications for floating, bottom fixed, and onshore cases, it is anticipated that there will be a 17% to 35% reduction in LCOE by 2035 and a further 37% to 49% reduction by 2050. Several factors affect these cost reductions, such as technological advancements, ongoing operation and maintenance optimization, grid integration, and infrastructures, and more. Additionally, reducing the cost in wind power generation depends in a large extent in understanding and mitigating the effects of turbines and farm wakes. In this video, I will focus very briefly into the impacts of wakes within the wind park and how wind energy production by the means of the energy yield of an individual wind turbine and the power production of a wind park. Let's now dive right into the energy production of a single turbine and then wind park. I will then explore the role of wake in energy extraction, but first few backgrounds and basics. Power curves typically depict the relationship between wind speed as shown in horizontal axis and the power output of wind turbine shown in the vertical axis. The curve shows the turbine's cut-in wind speed, which is the minimum speed at which turbine starts generating power. The rated wind speed, which is the optimal speed for maximum power output, and the cut-out wind speed, which is the speed at which the turbine shuts down to protect itself from excessive wind speeds. The power curve helps to understand the characteristics of turbine's performance and its ability to generate electricity at different wind speeds. Wind histogram is another important aspect that represents the frequency or probability of wind speeds as a function of wind speed occurring at particular location over a given period of time. For a turbine study, the wind histogram helps to analyze the wind resource and to estimate the energy yield. The wake of a turbine in a wind farm refers to the turbulent airflow that is generated downstream of a wind turbine due to the interaction between the rotating blades and the incoming wind. As the wind passes through the rotor of the turbine, It experiences changes in velocity and direction. These create a region of disturbed airflow behind the turbine. This region is commonly known as wake. It can be measured by different sensors and modeled by various wake models. The energy yield of a wind turbine is typically calculated using the following formula. The power output is calculated based on the wind speed experienced by the turbine at a specific point in time. The time refers to the duration for which the wind turbine operates and generates power. It can be expressed in hours, days, months, or years, depending on the selected time frame. In this formulation, it is then clear that the actual energy yield of a wind turbine can be influenced by various factors, including wind availability, turbine downtime for maintenance, grid availability, and other operational considerations. The annual energy production of a wind turbine can be calculated using the following formula. The integration in this formulation involves integrating the power output of the wind turbine over a range of wind speeds. The integration is performed by multiplying the power output at each wind speed by the probability density function of the wind speed distribution, as explained in previous slide. The capacity factor represents the actual energy production of the wind turbine compared to its maximum potential. It takes into account factors such as downtime for maintenance, grid availability, and other considerations. The capacity factor is expressed as a percentage and is calculated by dividing the actual energy production by the maximum possible energy production if the turbine operates at full capacity throughout the year. I now move from a single wind turbine to a farm. The energy production of a wind farm is typically higher than the energy production of a single turbine. There are several reasons for this. In a wind farm, multiple turbines are placed to capture the available wind resources. As a result, the total power output of all turbines adds up together. This naturally leads in generation of more electricity from the same wind resource. Wind farms are designed and operate to maximize their capacity factors by optimizing turbine placement, considering the availability of wind resource, and reducing downtime. And in short, a higher capacity factor results in a larger annual energy production. Wind farms employ various strategies to mitigate the effects of wake between turbines. I will explain this in the next slide. There is another factor I did not put here associated with the effects of economics of scale. As the size of a wind energy project increases, the cost of energy produced decreases and wind farms benefit more. This is because larger wind farms can take economic advantage of, say, bulk purchasing of components and shared infrastructures and so on. This makes wind farms economically more attractive. Let's talk briefly about wake effects on wind farms. Wakes can significantly affect the annual energy production of the turbines because in the downwind area of a wind park, we have a decrease in the wind speed. Since the power output of a wind turbine is proportional to the cube of the wind speed, even a small reduction in wind speed can result in a significant decrease in power production. Wake also introduce increased turbulence in the downwind area. Turbulence can negatively affect the aerodynamic efficiency of the turbine blades, leading to decreased energy conversion and increased loads and fatigue on turbine components. This by itself leads to lower energy production and increased maintenance requirements. As can be seen in this figure, the wakes can also cause interference between turbines, leading to additional losses in energy production. For example, if the rotor of a downwind turbine is located partially or fully within the wake of an upwind turbine, it can experience reduced wind flow and decreased power generation. As it has been clear so far, the exact impact of wakes on energy production can vary depending on factors such as wind farm layout, turbine design, wind conditions, and operational strategies. The question is, how can we mitigate the wake effects? To mitigate the negative impact of wakes on energy production, wind farm layouts and turbine spacing are carefully designed. By optimizing the spacing between turbines and considering the prevailing wind direction, developers are able to minimize wake effects and maximize overall energy production. Wake models are in general very important for several reasons. They significantly assist in optimizing turbine placement, determining the optimal distance between turbines, and evaluating the potential power losses. Furthermore, advanced control strategies such as wake steering and wake redirection are being implemented to further mitigate the impact of wakes and improve energy production in wind farms.